Hello, IB Physics kids. It's Mr. Kima here. This is part two. So 2.1 motion, one-dimensional motion, part two. And just start out with here, it says, Miss O'Malley, in case you weren't thinking about grading our science test on a curve, I prepared some templates you might find handy. Here's one where everyone fails except for me. Here's one where most people failed except for me. And here is the only one, or here's the one. The test was so hard, everyone quits except for me. He goes, you emailed me this over the summer, Jason, already repeatedly. Oh, you didn't respond, so I wasn't sure you got them. But the point is, just by looking at graphs, we can do a lot of looking, shall we say, at data without even doing any kind of math, okay? So for example, just by looking at this graph, if you can look, and I apologize because that thank you is popping up at the bottom, but the idea is the velocity is the highest at which point? Well, that would be point B. That's correct. It's all the way up there. Okay, and where's the velocity the lowest? Well, that's at C. And then A would be at the second highest, okay? So again, we got to look at what's called the slopes of graphs, and you guys should know that, okay? You guys should know that slope really means change in, okay? In this case, position or displacement. X marks the spot, displacement over time. Okay, so this would be a positive constant velocity, positive or negative constant velocity. Okay, no velocity and a changing velocity because the slope of a position versus time graph is velocity. Okay, so here we go. Here comes some horrible drawings right here, some horrible drawings. But let's just take, for example, if I had a distance or displacement versus time graph that looked like this. Okay, I'm trying to draw it the best I can. How would we solve this? Well, the best way to understand this, okay, is we have to first describe the motion, okay? And now what I always like to do is I like to chunk it into parts if I can. So like this would be part one, this would be part two, and this would be part three, okay? So let's think about what this is, displacement versus time. Well, this means this person is walking away at a constant velocity. They stop, but time continues to move forward. So some people say, well, if it stopped, why is it moving? Well, it's not really moving. It's just that time continues to move forward. And then that person is walking or going backwards to the origin. And we're going to say that that's at the same velocity as it was before. Okay? So if we think about it, displacement or x versus t, how do we get to a velocity versus time graph? Well, if we think about the slope of this graph is actually x over t, displacement over time. Well, a change in displacement over a change in time is actually equal to velocity. So if we take the slope here, if I can write, there we go. If we take the slope, we can then figure out the velocity. So we have 3 parts over here. So I'm going to put 3 parts over here, just in chunks, so that way we remember. Just like that. All right, so here comes our 3 parts. So don't even look at 2 and 3. Just look at number 1. Does it have a slope? The answer is yes. Is it positive or negative? It's positive. If we gave it a value, we could just give it an imaginary value of, let's just say, positive 1. So I'm going to come over here, and if it's at 1, I don't start down here. I start up here, and we're going to say it's constant. It's a constant at 1. This thing, if this was like a speedometer in a car, would kick up to 1 meter per second, 1 meter per second, 1 meter per second, 1 meter per second, and then what? Look at part 2. Does it have a slope? No, it does not have a slope. So how do we represent that? Well, that's the value of 0. So we say that this thing instantaneously jumps. We're assuming it takes no time to jump, and we put it down here at 0 on the x-axis. Then finally, that person had no velocity, and then they had, does it have a slope? Yes. Is it positive or negative? It's negative. And we're going to say it's equal but opposite. So we're going to say that that's -1. So we know we need to come down here and we need to be this distance away here, but in the negative. So we can look at that. All right. Hopefully that makes a little bit of sense. If for some reason this guy was, let's say, uh, it wasn't the same kind of slope, but it kind of went like this. It kind of stretched out farther. It took longer time. That's a lesser slope. Then our new line would be lesser in the y. Okay? Hopefully that makes some sense. Hopefully you're remembering that from physical science. So on a curved line, well, we can't just take the slope of something. We take we take this part, which is called that instantaneous velocity, or we take the tangent of this. Okay, and remember, a tangent, we draw our best fit kind of line right there, and then we take the slope of that line. Okay, hopefully you remember that. So again, we can look at a curved line and say, hey, what is happening to this velocity? Well, this velocity had a very low velocity slope, and now it has a very high velocity slope. So we say the velocity is increasing, okay, exponentially. All right, acceleration. So we've already done um, position versus time, but let's also do acceleration versus time. Okay, so we're going to do this. Here's our time graphs. Okay, going to put these all on here. Here we go. So these three lines down here represent these cars up here. All right, so one of these cars is A, one of these cars is B, and one of these cars is C. See if you can take a guess by looking down here what those cars are. All right, sometimes drawing a motion dot diagram will help you. Okay, so if you look at this red car, and again, excuse my dots, this red car is going at a pretty constant speed. It just kind of goes and goes and goes at its normal constant speed. God, those dots are not straight, but there you go. Our green car kind of starts out a little slow here, but then that green car starts picking up faster and faster and faster. All right, and then our blue car is the speed demon on Sawmill Road or 270, just flying off the screen here. Okay, so maybe that'll help you. Maybe now see if you can figure out which car is which car. All right, hopefully you figured that out. But the red car is actually car B. The green car is car C, and the blue car is car A. And hopefully you can see that. So car A takes off really fast. Car C um, takes a little bit more time to get going, and car B is nice and constant the entire time. Okay, so if let's just do this real quick. If car B is the red, oh look at this, look at this, look at me, such a great teacher. Okay, car C would be the green, and let's get here in the blue, and that would be car A right there's in the blue. Okay, so now let's go back and let's do car B, which is the red car first. So remember to get here, we need to take the slope. Okay, we need to take the slope because the slope of a velocity versus time, or the derivative of a displacement versus time, will get you velocity. Okay, so let's just look at B. All right, B, does it have a slope? The answer is yes. Is it positive or negative? Positive, and it's constant. So we're going to give it a value. We're going to come over here and we're going to give it a value, a nice constant value of let's just say 1 or 2 or whatever we want to call it. Okay? Now, let's look at A. Let's look at A, the blue car. The blue car. We kind of say we draw little tangent slopes here and we say, look, that slope starts at 0 because it's flat down here. I know it's a little hard to see, but it's flat. So we start at 0 and then it gets more and more and more and more. So it starts at 0 and it gets more and more and more and more. All right, it has a changing velocity. Its velocity keeps getting faster and faster and faster. Okay, now let's look at the green car. And my question to you with the green car is it going to look more like the red or is it going to look more like the blue? Well, the answer is it's going to look a lot more like the blue. Okay, but it's going to be different. It takes more time to get going. If I drew mini slopes, we'd have 0, 1, 2, 3 instead of 0, 2, 4, 6, whatever. Okay, so again, start at 0, and my slope's going to look similar to blue, but it's not going to be as steep because it takes more time. Alrighty then. So now go back. To get from a velocity time graph to an acceleration time graph, which acceleration is just literally a change in velocity. When you step on the gas pedal of your car, we call that the accelerator. Okay, that is a velocity over time equals acceleration. So the slope of a velocity versus time, or the derivative of velocity versus time, is acceleration. So let's look at this now. Now we no longer look here. We're only looking here. Does the velocity of the red car ever change? Is there a change in there? What is the slope of this red line? The answer is 0. There is no change. And if you think back to the first thing, this car is moving constant. This car has a constant velocity. If it has a constant velocity, then it's not accelerating. Okay? So now we go to the blue. Now we go to the blue. Does it have a slope? Yes. Positive or negative? Positive. Give it a value. Well, let's give it a value of, I don't know, 4. I don't know. Whatever. Just put a value up here. Imagine that was a nice straight line. Oh my goodness. Sorry about that. All right. Now, the green one, is it going to look like the red or is it going to look like the blue? Well, it's going to be like the blue. It has a slope, but it's not as high up as the blue. So let's just put her in the middle here. Okay. Somewhat straight line there. But if you actually go back and think, what is it asking? Does the blue car have acceleration? Absolutely. It has a curved line. It is accelerating. It's constantly changing. Does the green? Yes, it's constantly changing. Does the red? No. It is nice and constant. It is not changing. So that is why. And again, how do we get there? We take the slopes to move forward. There we go. So graphs with 0 constant, 0 acceleration, positive acceleration, negative acceleration. So if we look at this velocity versus time graph, what do we got going on here? Positive, negative, or no acceleration? The answer is no acceleration, 0 acceleration. There is no slope. There is no change. This velocity would be negative. Or excuse me, this acceleration would be negative. Okay. So here is our classic cop car problem. So the blue car is you on 270 speeding along. Okay. Look at the motion dot diagram, moving around. Okay. Here's the cop who is parked, and the cop sees you, guns it, and goes around you. Okay. Or you can think of it as here's somebody on 270 with their cruise control set at 70 miles per hour, and you're getting on from the on ramp. Okay. What's cool though is if you actually look and see the charted data down here, it's very easy. You can calculate the acceleration. You can tell me that the red car is now moving at 12 meters per second. The blue car is moving at 10 meters per second. Okay. You can actually see where they overlap, and that would also tell you where the intersection was. This car passes the other car at like almost 3 seconds or 2.5 seconds. Something I'll never test you on, but just like to talk to you about, wooden roller coasters. Hopefully you've ever noticed if you've ever went and ridden on a wooden roller coaster, it sways more. They say it's a rougher ride, and that's because wood gives a little bit more. So we can't really hit, like when we say no loops, we're talking about like inverted loops like that. Okay. And when we say steep hills, we're talking about like the Maverick up at Cedar Point where you're like inverted at 95 degrees. You don't see that with wooden roller coasters because we can't change our velocity quick enough. Now, when you get to steel roller coasters, like Steel Vengeance up at Cedar Point and all that kind of stuff, now we're able to change our velocity so quickly that we can do things that we never thought was going to be possible before. So The old wooden roller coasters are pretty much just hills. Maybe there's a slight turn, stuff like that. But the steel roller coasters now, since they can change your velocity and have such a high acceleration, they can do things that other ones couldn't do before. And then again, you're going to have some homework problems, and you'll see that all in there. Okay, guys, I know the notes were a little long. It was thank you for not being mad about my drawing. Other than that, have a great day, and we'll see you next time.